So guys, let's try this again. So what we're going to do today is we're going to take the stuff that you just graded, which apparently you're really good at because your scores were good and you asked no questions. And we're going to build on this idea of mass problems, and we're going to add one additional layer to the onion, which is percent yield. Sounds a lot like percent error. It's actually the opposite of percent error. So we're going to talk about the concept, we're going to talk about the math, we're going to solve a problem. And guys, what you're going to see is that when I see you on Thursday, and I just want to tee this up for you right now, this is the lab that we're going to do on Thursday. But during professional development day yesterday, Miss Call and I had an amazingly productive day. We've written the test for this unit, and we've written all of the remediation materials because we've got to have them done because we're running into the end of the quarter. So guys, I already know what's on the test, and I already know what we're going to remediate. And guys, on the test and in remediation, the lab is going to be in there. So the lab that you're doing on Thursday will be the last page of the test. And if you don't understand it, it's also one of the things that we're going to remediate. We've decided that this is a good time to actually make you accountable for being able to work effectively in lab. But guys, the reason that I mention that now is because it all builds on this idea of percent yield. So that's where we're going to start. Then guys, when we're done with percent yield, we're going to call time out, and we're going to talk about an unrelated concept, which is called limiting reactants. So these are two separate concepts. This is how we wrap up the unit. And again, you're going to need note-taking materials, calculators, periodic tables, and obviously something to write with. So you guys ready to go? You okay? All right, so guys, don't write this down, but here are our goals today. Obviously, we're going to talk about percent yield and limiting reactants, but these are actually, and again, don't write it down, these are the questions that we're going to answer. We understand that reactants turn into products. That's how reactions take place. The questions that we're going to answer today are actually two. Question number one is this: how much product should a reaction make? So if we know how much reactant is going in, how much product should that reaction make? And guys, that is what is called a percent yield calculation. Then guys, the next question that we're going to ask is this: when do reactions stop? We understand that reactions don't go on forever. If you're burning a match, eventually the match goes out. Guys, when do reactions stop, and how can we calculate how far they go? So guys, these are our two questions, but actually these questions are these topics. How much product should a reaction create? Percent yield. When does a reaction end? Limiting reactant. So the answers to these questions are these topics. So let's get started with percent yield. So guys, get this in your notes. So what is percent yield? So guys, percent yield is simply a ratio. And when we talk ratios, what are we talking about mathematically? What kind of math is a ratio? Division. So guys, this is a ratio that compares the actual amount of product that a reaction did make compared with the amount of product a reaction should produce. And guys, the equation looks like this. Oh golly, one too many clicks. The equation looks like this. We did not put this on the test, but if you remind me before the test, I'll write it on the board. You don't have to memorize it. It's pretty simple, but we'll give it to you. So guys, it says this: percent yield is equal to the actual yield divided by the theoretical yield times 100. So let's define our terms. The actual yield comes from the experiment. And then, guys, the theoretical yield is predicted by a mass problem. Guys, while you're writing this down, sorry it's on my mind, thinking about tomorrow, and I know you're sick of hearing this, but I don't care. So we are going to cycle tomorrow, but the second Wednesday of each month, we actually are doing classroom sessions before we train. So tomorrow at 3 o'clock, I'm actually teaching a little 20 to 30 minute class on preseason training strategies. So if you're interested, come. We are still going to ride. We're just going to go down and ride at 3:30. So come if you'd like. We had like 12 people train with us last week. It was really cool. You guys all caught up? You done riding? So guys, let's talk. Looks familiar, right? What does it look like? Percent error. What's missing from percent error that's not here? Go ahead, Kat. The subtraction, right? So guys, if you look at percent error, it's actual minus theoretical divided by theoretical. In this equation, we're missing the subtraction. So what's the difference? Well, guys, percent error, because of the subtraction, is calculating how much you got wrong. Percent yield, because it's missing the subtraction, is actually calculating the percent you got right. So they're actually opposites of each other. So if you calculate the percent yield and the percent error for a reaction, what do they add up to? 100. You get the idea? Okay, so guys, here's what we know. The actual yield, and this is what you're going to do in lab on Thursday. You're going to do a lab and you're going to weigh the product. The actual yield comes from experimentation. The theoretical yield, you've got to calculate from a mass-mass problem. But guys, we just graded homework over mass-mass problems, and apparently you're good at them. So this should be pretty straightforward, because once you know this, you plug it in here and you just do the division. So guys, how do we solve these problems? These are the steps, and then we're going to solve one together. So guys, step number one, which is really the first step in solving a mass-mass problem, is you need a balanced equation. Then guys, once you've got your balanced equation, it's now time to do the mass-mass problem. But this is where this gets a little different. When you start your mass-mass problem, you're going to have two options in terms of where you start. You will always start with the mass of a reactant. Then you will set your goal at the mass of what we call the known product. And this will make more sense in a minute. Then guys, step 4 is you solve the mass-mass problem, which is functionally the homework that you just graded. And then guys, all we got to do is add step 5, which is simply to use the result of this mass-mass problem as the theoretical yield in the percent yield equation. So guys, once you've got this written down, we're going to solve an example. But what you're going to see is, rather than have you watch me solve this example, you're going to find that I actually typed it, but I typed it and animated it in such a way that hopefully it'll help your eye track how these numbers are moving around within this problem. You'll see. So guys, we'll solve this. Then we're going to talk briefly about the concept of limiting reactants. We're going to be done in about 15-20 minutes. And then you'll have lots of time to get your homework done. Well, I don't know if you'll get done, but you'll get started. And guys, remember too, if you're missing homework from the current unit, all of that homework will be turned in by Thursday. There won't be any homework due dates after Friday, which means that if you want to turn in missing homework assignments, and again, only from this unit, because you can't turn in homework after you've taken the test from previous units, you got to get that to me by Friday too. You guys all caught up? You okay? You good? Can I go on? Okay, so guys, let me show you how one of these works. This is going to feel really familiar based on what you learned to do with mass-mass problems. It's just that there's one thought that has to go into this up front in terms of your starting point, and then there's that last additional calculation that's just percent yield is equal to actual divided by theoretical. So you may want to write down this equation, or this question. Says this: you take 15.5 grams of methane. And guys, you've probably noticed by now that when I give you example problems, I try to tie them back to reactions that you've seen before, and burning methane is one that we've talked about a lot. It was conclusion question number 3 in the lab that you just turned in. This is what happens in your Bunsen burner. But guys, the question is this. When 15.5 grams of methane is combusted with excess oxygen, 32.1 grams of water is collected. How'd you do? What's your percent yield? So I'll let you write it down. And actually, you know what? While we're at it, let me just give you this as our starting point. Here's the balanced equation. You've written this balanced equation like 7 times now. So I'm pretty comfortable just giving it to you. Are you good? You okay? So guys, let me read the question to you one more time. Here's what it says. It says, when 15.5 grams of methane, Bunsen burner gas, is combusted with excess oxygen, you get 32.1 grams of water. What's your percent yield? So guys, don't write any of this down, but let's talk about what this means. So guys, first of all, what does it mean if something is in excess? What does that mean? You got extra. You've got all you need and more. So guys, the idea is this. If you have a limited amount of methane, so if you have 15.5 grams of methane, and you've got all the oxygen you need to burn up that 15.5 grams of methane, and when you do this, if you collect 32.1 grams of water, how much did you lose? What's your percent yield? Is that good? Like, should you have collected 32.1 grams of water and that's exactly how much you should have got? Or should you have collected 100 grams of water and you lost 2/3 of the water you should have produced? Now guys, to answer that question, what do we need to know? How much water can we produce? So guys, the question we've got to answer is this. If we've got 15.5 grams of this, and all of this we could ever want, how much of this can we produce? And then we'll compare that to 32.1 grams and see how we did. You get the idea? Okay, so guys, let's solve it. So the first thing that we want to do is we want to go to our question and we want to gather together the information, just the same way as I showed you to solve mass problems. So guys, let's gather this information. So we've got 15.5 grams of CH4. So, oh, I think I'm drawing dots. So 15.5 grams of CH4, let's write it down. But now guys, you'll notice the thing that makes this question unique is that we have another mass. We've also got this mass, which is 32.1 grams of water. And I think you'll find it very helpful to organize like this. Because now, guys, we've got our balanced equation, step 1. We've gathered together our information. So now, guys, look at step 2. What does step 2 tell you to do? Well, set up the dimensional analysis. So let's draw a line, and let's get ready to do some dimensional analysis. How long does this line need to be? How many calculations will go on the line? 3. Mass to moles, moles to moles, moles to mass. These are always the same. But guys, where are we going to start? Are we going to start with the 15 grams of CH4 or the 32 grams of water? How do you know the 15.5 grams of CH4? It's the reactant, guys. And so, check this out. So guys, we know that CH4 is the reactant. Watch this. So that is the mass that we start with. Now guys, the next thing that we need is this. Again, we're always starting with the mass of a reactant. Now we need to know our goal. Step 3. Guys, what is our goal going to be? Grams of what? Grams of water, grams of oxygen, or grams of carbon dioxide? And why water? Notice the way step 3 is written. It says set your goal at the mass of the known product. And guys, water is the one that we know something about. So our goal is going to be grams of water. And now guys, we just have to do the mass problem. Again, homework just like before. You guys are demonstrating mastery of this concept because your homework scores were good and you didn't ask questions. So it's a 3-step process. Step number 1 is grams to moles. CH4 is 16 grams, 12 plus 1 times 4. Then guys, the next step is the mole to mole ratio. As you know, it's moles of CH4 on the bottom, moles of your goal water on the top. So now guys, where do we get the numbers to fill in the blanks? From the balanced equation. We look at CH4, there's no number in front, so what do we understand that to be? A 1. And then on top, in front of the water, we've got a 2. And then guys, converting then moles to grams, we understand that 1 mole is then the formula mass of water. Oxygen 16.0. Hydrogen is 1, and that's 18 grams per mole. And then guys, we do the math. 15.5 divided by 16 times 2 times 18, and that's 34.9. So guys, all of that was the last homework assignment. So now we need to talk about the new stuff. So here's what we now know. We now know that if we put in 15 grams, 15.5 grams of CH4, all the oxygen that we need, we can make 34.9 grams of water. But did we make 34.9 grams of water? No. How much did we make? 32.1 grams of water. We lost some water. So let's figure out not how much we lost, because that would be percent error. Let's figure out how much we captured. That's percent yield. So guys, we go percent yield is equal to actual divided by theoretical. Is that too low on the screen? Can you see it okay? So guys, now we need numbers. I would encourage you to watch the screen because this might help. So guys, first thing we need is the actual yield for water. Where do we find the actual yield for water? Right here, so we bring that number down. Our actual yield is 32.1 grams. Now guys, where do we get our theoretical yield? Right here from the mass problem, so we bring that number down, and then we do the math, and we get 92%. That's pretty good. Now guys, can I let you in on a little deep, dark secret that's going to be one of the conclusion questions on your lab on Thursday? Why would it be impossible to have more than 100% yield? It is impossible. Why can't you have, what does it mean if you have more than 100% yield? You created matter. You can't get more than you theoretically should. So guys, what law is that violating? The law of conservation of mass. You cannot get more than 100% yield. But guess what? Half of you probably, around half, if you guys are average or typical, half of you, when you do the lab on Thursday, your percent yield is going to be higher than 100%, which does not mean you just became a god with the ability to make matter. I know, right? Someday. But, so guys, the question then becomes this. What explains higher than 100% yield? Because a lot of you are going to run into this on Thursday. How do we explain it? Say it again. No. Wrong. It could be wrong calculations, but that doesn't explain it. It just means do the math right. Yeah. Talk more about that. What are you thinking? Okay. Yeah, okay, so I think you're barking up the right tree. It wouldn't be the oxygen, because the oxygen's got to stick to the hydrogen to make water, and or carbon, and any oxygen that doesn't stick will just go away. But what's the underlying principle behind what you're saying? There's something in there that isn't just water. And guys, we call those contaminants. So if you get higher than 100% yield, it doesn't mean that you're making matter. It means that your sample is contaminated and there's something in there that isn't actually your product. Maybe not oxygen, but the idea is good. You get the idea? So guys, there you have it. Percent yield. This is exactly what you're going to be doing in homework and exactly what you're going to be doing in lab, with the one exception that you will not be given the mass that you start with. You will not be given the mass that you end up with. You'll actually be weighing things in lab. But other than that, guys, that's what you're doing on Thursday. You guys groovy? Okay. So guys, call timeout. Switch gears. We are now going to talk about limiting reactants. We are now going to answer the question, when do reactions stop? When do chemical reactions finally give up? So, guys, the idea is this. Take a match, light it on fire. What's reacting right now? Oxygen and paper. And it's about to become oxygen, paper, and my finger. I should have got tweezers. What am I going to do? No, I'm not going to wait. So you know eventually this is going to burn out, right? Ouch. Okay, so eventually that would have burned out, right, had I not blown it out because it was starting to hurt me. But guys, if I had allowed that to burn out rather than me blow it out, guys, why does the match eventually go out? You run out of paper. Thankfully, you don't run out of oxygen. But guys, many times that's actually why people die in fires, like house fires. You suffocate because the fire is consuming oxygen so rapidly that there isn't enough oxygen left in the house to breathe. But for something like this, understand that this flame goes out because we've run out of the paper. And that makes the paper what we call the limiting reactant. That is the substance that you run out of that then limits, thus the name, how far the reaction can proceed. So, guys, with that in mind, let's formally define the term, and it goes like this. The limiting reactant is the reactant that is completely consumed in a chemical reaction. In the example of the match, it's the paper. So, guys, of course, we call it that because it limits the extent to which this reaction can go on. Next class, I'm going to have tweezers ready. All right. So, guys, maybe we should talk about this. You know what? I'm going to add it to the notes. So, we understand that the limiting reactant is the thing that limits the extent of the reaction, right? So, what's the other one called? And you already know. It was in the previous problem. So if the limiting reactant is the one that you run out of, the one that's not limiting is called the excess reactant. Oh, thank you. There we go. Thank you. Oh, one click too. Oh, hello. Whoa. Oh. There we go. The other reactant, the one that's not limiting, is called the excess reactant. So guys, your challenge then becomes this. Given a reaction and given an amount of reactants, your challenge is going to be to figure out which one you'll run out of first. That's funny, this girl's not in this class. Yeah, not for me. So guys, what I want to do, this is pretty brilliant. What I want to do is I want to show you graphically this concept of limiting reactants. Now, the problem is that it's hard to see atoms. You saw the match go out. But guys, when you think about a match in a room full of oxygen, it's pretty obvious which one the limiting reactant is going to be. What if we're looking at chemical reactions that you can't directly visualize and the amounts are not that dissimilar? How do you know which one we're going to run out of first? Well, guys, I'd like to show you by introducing you to a chemical reaction. Don't write any of this down. Just watch. Just trust me. Just watch. So, guys, the reaction goes like this. Fluorine, W, which is interestingly tungsten, because we used to call it wolfram, and sulfur yields bismuth. What kind of reaction is this? Synthesis reaction. How do we know? One product. And so guys, we also have the molar ratio in this reaction, right? It's the stoichiometric ratio. It's 1 to 2 to 1 to 1. So synthesis reaction, and this is the reaction that we're going to study. Good? Guys, if you take fluorine and tungsten and sulfur and stick it together, are you going to get bismuth? No. That would be a nuclear reaction. And you can't stick elements together like this to produce new elements. So guys, what does this represent? Well guys, what do chemical equations represent? Reactions, things sticking together. And this does in fact represent things sticking together, but interestingly, this is not the recipe for bismuth. This is the recipe for bicycles. To build a bicycle, you need one bicycle frame, you need 2 bicycle wheels, and you need 1 bicycle seat. This is wildly oversimplified, but if you stick those 3, 4 things together, you're going to get a bike. Kind of. But, guys, this is where this becomes a wonderful analogy. So imagine this. Imagine that you're looking for a summer job, and we'll take Jameson because my eye fell on him first. And Jameson's like, I want a summer job. I really don't want to flip burgers, although there's nothing wrong with that. So I'm going to go down to Mad Dog and I'm going to see if I can get a job at a bike shop. I like bikes. It'd be a fun environment. I'm going to go work there. You walk into Mad Dog. You talk to the owner and say, hey, could I work for you this summer? And they say, yeah, we need somebody. Come on, we'll give you a job. Well, guys, understand that if you get a job at a bike shop with absolutely no skills, and Jameson may have skills, but if you have no skills, you're not going to be fixing bikes and you're not going to be talking to customers. They're going to lock you in back and they're going to have you build bikes. But guys, they're not going to have you build their nice bikes. They're going to have you build their $30 bikes that they may as well sell at places like Walmart. So nothing wrong with Walmart bikes, but understand there's different levels of quality. And guys, the thing that you don't know is that when a place like Mad Dog buys their low-end bikes, they don't buy the bikes. They buy bike parts in huge crates that get shipped over from China, and they build their bikes by just putting the parts together, kind of like this. And guys, we're going to say, and we know it's oversimplified, that a bike is simply a frame, 2 wheels, and a seat. So Jameson gets the job. Jameson walks into the very deep backest part of Mad Dog Cycles, and he walks in there, and there are these huge boxes full of bike parts. But guys, the thing that's crazy is these bike parts are so cheap that instead of buying parts by the piece, you buy parts by the pound. And when Jameson walks in there, these things are labeled. And he's got 120 pounds of bike frames. And he's got 100 pounds of wheels. And he's got 50 pounds of seats. Here's the question I have for you. How many bikes can Jameson build? Depends on, say it again. Right. Do you understand that logic, guys? We can't answer the question because we don't build bikes by the pound, we build bikes by the part. Remember how in the last 3 labs we've been talking about this idea of particle ratios and mass ratios? This is a particle ratio, 1 to 2 to 1, not a mass ratio. So we don't care what these things weigh. We need to know how many parts this represents. And as Lila said very well, how many parts depends on what they weigh. So what if I then told you this? What if I told you that frames weigh 20 pounds, wheels weigh 10 pounds, and seats weigh 2 pounds each? What can we do with those numbers to help us figure out how many bikes we can build? Divide. So guys, when we go through and do this division, we have 6 frames, 10 wheels, and 25 seats. Make sense? Okay, now how many bikes can we build? Now we got a problem. Is it 6? Is it 10? Is it 15? I hear some people saying 5. Guys, I don't even see the number 5. So talk to me about 5 because that's really not obvious. Go ahead, Robert. So now we need to account for the fact that it's not one of these, one of these, one of these. We need to account for the fact that we need 1 frame, 2 wheels, and 1 seat. So now what we do is we divide by their relative numbers of things, respecting the fact that we need 2 wheels. And now we have a 6 to 5 to 25 ratio. Now how many bikes can we build? 5. And guys, when we're done building those 5 bikes, if we look down in the crate of wheels, what's going to be in there? Nothing. What's going to be in the frame and the seat boxes? Extra stuff. So guys, the box that empties out first, in this case the wheel box, is going to be our limiting reactant. Because that's the thing that you run out of first. That box is empty, and what does that make the seats and the frames? Excess. You get the idea? Okay, but guys, notice how we did this. This makes wonderful logic when you're thinking about bicycles and parts. But the same logic applies to atoms. Notice what we did first. We had to account for the fact that these don't weigh the same. So we had to account for their different masses. Then we had to account for the fact that it doesn't take 1 of each, so we had to account for their stoichiometric ratios. Guys, that's exactly what we're going to do with chemicals. Let me give you the steps. Write this down. So guys, when we calculate limiting reactants, here's what we do. Step number 1 is this. Write a balanced equation. We're doing a lot of that now, aren't we? Step number 2 is convert to moles. This accounts for their differing masses. Because when we convert to moles, we're dividing by their formula masses in the same way that we were dividing by the weights of the frames and the seats and the wheels. By the way, a 10-pound wheel is ridiculously heavy. A good set of wheels weighs about 4 pounds. Then guys, step 3. You're going to divide by the coefficients from the equation. In the same way that we divided by the 1 and the 2 and the 1, and this accounts for their differing ratios. And then guys, at that point, the smallest number, just like with the bikes when we said 5 bikes, the smallest number is your limiting reactant. Wasn't that a good analogy? I know, right? Yeah. To be honest with you, Robert, the tungsten and the fluorine and that was completely coincidence. I just put it up and then I went, wait, that's fluorine and tungsten and bismuth and silicon. Yeah. It just got better with time. Okay, so guys, we're going to do this, but here's the thing. Not only are we going to solve one of these, but I'm going to show you a structure that allows you to solve this. Here's the problem. It's going to look a lot like calculating empirical formulas. Remember when we did empirical formula calculations? We started with the masses, converted to moles, divided by the smallest number of moles. That gave us the ratio. We're going to structure this similarly, but don't get confused. So guys, here we go. 25 grams of HCl reacts with 25 grams of zinc to form zinc chloride and hydrogen gas. Which do you run out of first? I don't even think you need to write this down. Let's just solve it. So guys, here's the balanced equation. Single displacement reaction, that you probably want to write down. Balance is like this. Single displacement reaction. This is the reaction that you did in lab that generated the hydrogen gas that then led to the explosion. So guys, the question is this. 25 grams of HCl, 25 grams of zinc. You put them together, which do you run out of first? Some of you are right now thinking, we're going to run out of them at the same time because we've got the same amounts of both. That's not right. That would be similar to saying because we have 25 pounds of bike frames and 25 pounds of seats, we're going to run out of bike frames and seats at the same time. We know that that's not true because they don't weigh the same and they may not stick together in the same ratios. So we got to do the math. So guys, it goes like this. When we solve this, we're going to write down the masses one beneath the other, just like empirical formula calculations, but don't get confused. And we're going to do a one-step dimensional analysis problem. And guys, when you do these, be really careful. This doesn't make Miss Call and I bad people, but if you don't keep track of significant digits, the masses that we will give you on the test will be so close to each other that if you don't write down the proper number of significant digits, you're going to get the whole thing wrong. So guys, we've got to convert 25 grams to moles. It looks like this. Chlorine is 36.5 grams per mole, and we need 3 significant digits, so it's 0.685 moles of HCl. Again, guys, I know I'm going quickly, but I feel comfortable clicking through these simply because you've done these before. Then guys, zinc to moles is 65.4 grams as a mole, and there we go. Y'all caught up? Not quite. Okay, so now guys, let's talk. Which one are we going to run out of first? Which do we have less of, the zinc or the HCl? Which do we have less of? The zinc. We have fewer moles of zinc in the same way that we had fewer bike frames. It's just in moles rather than individual frames. We have less zinc. Physically, we have less zinc than we have HCl, but you're going, wait, they weigh the same. How could we have less zinc if it's the masses are the same? Zinc weighs more. But guys, we still don't know that we're going to run out of zinc first, because they don't necessarily bond 1 to 1. So what do we have to do now? Divide by the coefficients. In front of the HCl, there's a 2. In front of the zinc, there's the 1. The common mistake here is you're going to divide by the smallest number and figure out the empirical formula. No. Divide by the coefficients. So guys, we divide HCl by 2, we divide zinc by 1, and now the number that's smallest is the one that we're going to run out of first. We will, and guys, understand, if you stop here, you will not get full credit for this question on the test. Because the question doesn't say do math. The question says, what is the limiting reactant? And this doesn't tell you the limiting reactant. You have to interpret your calculation. So the smallest number is the limiting reactant. So you need to write down HCl as the limiting reactant. So guys, there you have it. We are now done for the day. You've got more than 20 minutes to work on your homework. This is assignment 5, which is the last homework assignment in this unit. Questions 1 through 5, these are all, well, 1 through 7, they're all percent yield equation. They're all percent yield calculations. 1 through 5, I gave you the balanced equation. 6 and 7, I did not. Then you'll notice there is a second page. Guys, don't miss the second page. Those are the limiting reactant questions. Guys, I will post the answers on the wall in just a moment. Let's get these done. Again, guys, we've got some things coming up today. If you're doing remediation, the remediation test is during Pride today. Make sure you've got your homework assignment done. Be here before noon. And then, guys, remember Friday's the cutoff for third quarter work. So, guys, dig in. Let me know if I can help. Go get them.